Hello everyone and welcome to today's webinar. On the behalf of American Petroleum Professionals of Iranian Heritage, APPIH, it's our great honor to start another webinar on the subject of practical machine learning applications in the oil and gas industry. During and after webinar, you can write your question in the chat box and please switch off your microphone and camera. Let's introduce today's speaker. It's our great honor that today we have Mr. Belyadi. He is currently a senior data engineer scientist with Wine Oil and Gas. He is also founder and CEO of HPP Solutions company focused on providing artificial intelligence services. Mr. Belyadi is also a joint faculty member at Marietta College and St. Francis University. He is also primary author of a famous book entitled Hydraulic Fracturing in Unconventional Reservoirs. He earned his bachelor and master degree both in petroleum and natural gas engineering from the West Virginia University. I would thank Mr. Belyadi for accepting our invitation, and without further delay, I'm transferring microphone to him for starting his webinar. Thank you.
Thank you very much. Appreciate it. Hello, everybody. Today, we're going to talk about some practical machine learning applications within the oil and gas industry. So with that being said, I just wanted to talk about first about the fundamentals of using machine learning, defining some of the terminologies first. Then we'll go in and talk about a couple of practical case studies that we've used in the past with good success within the oil and gas industry. So first, before we get into more detail, let's just talk about what machine learning is and why we use machine learning. So as you guys know, as the volume of data increases, human cognition is no longer able to decipher that information from the data, right? So if I have, let's just say if I have like 10 wells, if I have 5 wells, I can look at those 10 wells and analyze those wells pretty easily, right? Now, if I have 500 wells, if I have 1,000 wells, if I have 2,000 wells, then I will have a much harder time deciphering and finding pattern within that data, especially in the oil and gas industry where a lot of variables change. Like, for example, people do a lot of testing. They change multiple variables at a time. So it becomes very challenging to decipher information and pattern from the data. That's where machine learning comes in. Let's just define some terminologies first. First, let's talk about AI. So AI is basically using machine intelligence as opposed to using human intelligence or animal intelligence, okay? Now, machine learning is a subset of AI, okay? Is a subset of AI. And then, so let's just say, if I'm trying to train somebody to play basketball, okay? That's called machine learning, right? But if I'm looking for the best basketball centers, let's just say here in Dallas, Texas, that is data mining, right? So there are different terminologies that are interchangeably being used. I just want to make sure first we define the terminologies, then we go into more detail. And then they also use deep learning. Deep learning is simply a neural network with multiple hidden layers. There are different types of deep learning algorithms, such as convolutional neural network, recurrent neural network that are being used for different purposes, such as image classification and time series analysis and so on and so forth. Okay. So now that we understand what machine learning is, let's go and talk about different types of machine learning and what each type is used for. So the first type is called a supervised machine learning algorithm. Okay, so in a supervised machine learning model, what we're trying to do, we have a set of inputs, and we're trying to correlate and connect those set of inputs to an output or multiple outputs. It doesn't have to be one output. It could be multiple outputs. Okay, so let's just say I'm trying to, let's just say in the oil and gas industry. Okay, I'm trying to connect, like, for example, what type of impact my completions properties, my geologic variables, my well spacing, and so on and so forth, what kind of impact those parameters have on my output feature, which is in this case a production metric. Let's just call it EUR per 1,000 feet, okay? So my data is basically, it has a label, and that label in this case is a regression model because it has numbers which are EUR per 1,000 feet, okay? So that's a supervised machine learning algorithm. Or another example, let's just say if you guys are in the process of, let's just say buying a house, you go on Zillow and you see the Zillow estimate for the price of the house. Well, where does that Zillow estimate comes from? Well, what they've done, they've trained a machine learning model based on, for example, number of bedrooms, number of bathrooms, and square footage, and garage, whether the house has a garage or not. They've built a supervised machine learning model, and the output of that model is basically the price of the house. And once they have built and trained a machine learning model, they can predict when a new house comes on the market, what is the estimated price of that house. And that's where the Zillow estimate comes from. So we can use supervised machine learning like applications to solve different problems. It doesn't have to be just completions optimization. It could be chemical optimization. It could be anything, that there has to be some inherent relationship between the inputs and the outputs, okay? So that's supervised learning. The next one is called unsupervised learning. And in unsupervised learning, as opposed to supervised learning where you have a target class, in unsupervised learning, you have no target class, okay? You're just trying to cluster your data. You're trying to cluster your data to essentially place the data that are like together, okay? So in unsupervised, you have no target class. Example of, for example, using an unsupervised machine learning model in the oil and gas industry would be, for example, for type curve clustering. If you're trying to divide your regions like that you have into different clusters to see which areas perform similarly, you can use different types of unsupervised techniques, such as k-means clustering, density-based dB scan clustering. You can use hierarchical clustering, and so on and so forth. Now, the next one, before we go and talk about reinforcement learning, there's another one called semi-supervised. In semi-supervised, first you can train a model using an unsupervised learning algorithm. And in unsupervised learning algorithm, the output would be, this row of data is cluster 1, the second row of data is cluster 2, and so on and so forth, right? Once you have clustered your data, now your model becomes a supervised model. So now you can use that clustering column as your output into your supervised machine learning model. So first you tackle the problem, you solve, you cluster your data, then you can use that clustering column as the output into your supervised machine learning model to train a supervised machine learning model, okay? And then the third type is reinforcement learning, and that's basically the machine training itself on a continual basis. So today, I have an example on supervised, an example on unsupervised learning. I'm going to talk about completion design optimization using supervised learning, and I'm also going to talk about using unsupervised learning and k-means clustering to divide my data between a loaded versus unloaded condition. So let's talk about different algorithms within each type of machine learning like model. So first, under supervised, we have artificial neural network. It's called ANN. Support vector machine, very essential regression and classification machine learning model. K-nearest neighbor, very simple machine learning model, but yet very powerful, but it has its limitations. Random forest, we're going to talk about this like a little bit today for feature ranking. Random forest is a very popular model, supervised model used for feature ranking. Extra trees, and then you have decision trees, gradient boosting. These are just some examples of supervised learning. Now, unsupervised learning, as I said, k-means clustering is one example. Hierarchical clustering, density-based spatial clustering, and then you have the a priori algorithm. And then for reinforcement learning, some examples are Markov decision process and Q-learning. This is just to give you some perspective on when you hear these terminologies, some of them are supervised, some are unsupervised, and some are reinforcement learning. So now let's talk about a workflow for building these models. We'll talk about the workflow. We'll talk about the fundamentals of every single step. And I tried to summarize it as much as I could. But then we're going to go over some examples. So bear with me on this step, which is a very important step. So step number one is basically collecting your data, right? And again, it sounds easy, but a lot of times you have so much, you have so much data everywhere, you know. You have some data stored here, some data stored there, you know. So collecting that data is very difficult, right? So one approach that a lot of companies are taking right now is having a central data warehouse where all of your data are located in one central spot. So collecting that data is very easy, it becomes very easy. So right now, 80% of the time is spent, you know, collecting and cleaning data. But that 80% that I just quoted will go down over time as companies make things more automated, make things more kind of smooth, you know. You're going to spend much less than 80% of the time collecting and cleaning that data. You're probably going to spend, at least my vision is you're going to spend probably less than 10%, you know, collecting that data, because now all of your data is in one central place. You don't have to go to the different places to get that data. Now you can build different types of central data warehouses, you know, using SQL or other types of like applications. Okay, so once you collect that data from different sources or from one central spot, you can actually go and go to a second step, which is cleaning your data. Okay. Now, data cleaning involves a lot of different steps, and I'm going to go through that. I'm going to go to the next slide and then come back to the slide. So part of step, you know, 1, 2, and 3, part of data cleaning process is data visualization. It is so very important to visualize the data. A lot of ML models fail because, you know, people just go ahead and put in a bunch of information and run a model on it without even understanding what's in the data, without visualizing the data. So, you know, if you guys use Python or R, for example, there are various very powerful packages such as matplotlib, Seaborn, cufflinks, plotly, and so on and so forth that you can use to visualize your data. And by visualizing your data, simply do a distribution plot. Look at your distribution of your data. Look at a box plot. Look at a scatter plot just to see what kind of data you have. And also find the anomalous points. You might have a lot of, you know, like anomalies within your data. Like, for example, if you pump, you know, if on average your stage spacing varies from 100 feet to, let's just say, 300 feet, okay? And you have a data point that says your stage spacing was 600 feet. Well, you know that particular data point could be questionable, right? So you want to go back and make sure that you can remove those, you know, typos or anomalous points that you had in your data that you never actually pumped, you know. So data visualization is so important because you can see your entire data and really understand what kind of data goes into your model, and it can really sometimes it can really break your model. If you have a lot of anomalous points that are just garbage, you know, it can truly affect your model, and you can actually test it for yourself. So once you visualize your data, you're also going to have your, you know, you can, you know, find the anomalous points, right? Then the next step that is super important is called collinearity removal. Okay, so you want to remove parameters that are heavily collinear. Okay, which means those parameters provide you the same information. There is no need for repetitive, like, for example, parameters in your model. For example, if you have two geologic features that are pretty much provide the same thing, one is derived from another one, why would you include both parameters into your model, right? You want to make sure you remove the collinear parameters to remove, you know, any kind of to remove any kind of complexity from your model, because it's not necessary. You know, if one geologic feature provides the same information, why would you include another geologic feature that provides you the exact same information? You know, so that's the next step. Collinearity removal is very, very important step when you clean your data, when you try to select your features. Now, the next step is feature ranking and selection. I always tell people, try to simplify your model as much as you can. Use some features that truly have an impact on your model. You can do a feature ranking to see which features, fall at the, top of the tree versus at the bottom of the tree. The features that are not important, that fall at the bottom of the tree, I would try to remove those features, or at least remove them to see if it really has an impact on your model or not. If it doesn't, the more you can simplify it, the better off you are. There are different algorithms. We'll talk about random forests, extra trees. You can use different algorithms to really do feature ranking and try to select the best features. And also the feature ranking selection also goes back to your domain expertise. And we'll talk about that. This is a very important step. If you, for example, if you are working on a project in the oil and gas industry or in any industry, the very first step that I would recommend is to really understanding the problem, to make sure you understand the problem, to make sure you have the domain expertise, within that industry to really solve the problem. If you don't have domain expertise, that's no problem. Just get with somebody who has domain expertise, who you guys can combine your efforts to really truly build a successful model. Okay, and then the last step is feature normalization and standardization. Now, normalization and standardization varies. Some algorithms, like for example, when you use a neural network, it requires normalization. Some distance-based algorithms require standardization. Okay, so feature normalization and standardization essentially means you try to scale your features to be on the same level. So feature normalization is simply we're going to talk about the formula in just a minute. Is taking each x minus the minimum of x divided by max of x minus min of x. So you're trying to bring all your features to be between 0 and 1, and that way, if you have a feature that has a range of, let's say, 10 feet to 50 feet, and another feature that has a range of 1,000 to 5,000, you can bring all of those features on the same scale when you normalize them. And standardization simply means subtracting the mean and dividing that feature by standard deviation. So your data has a mean of 0 and a standard deviation of 1. Now that we understand these very important steps, these 5 important steps, let's go back to the previous slide. So we've covered step 1, 2, and 3 thus far. Okay, we've covered these first 3 steps. Now the next step is simply before you train a model, we've got to do a cross-validation, which means you split your data into a training set and a testing set. Okay. Let's just say you have 1,000 data points, okay? I'm gonna take those 1,000 data points, I'm gonna take 700 points, okay? And use 70% as my training, and I'm gonna use the remaining 30% as my testing. Like for example, in this case, okay? You could do a 70-30 split, 80-20 split, 90-10 split, depending on what you're trying to do, okay? Let's just say I'm gonna pick 70% for training, 30% for testing. You train a model, okay? Using whatever algorithm that you're going to use, right? Based on the problem that you have on the training data set, okay? And then you apply it to the testing set to see how your model performs. Now, if the accuracy, let's just say the R-square accuracy, like for example, on the training set is 95%. Now you apply to the 30% data, your R-square accuracy went down to, let's just say, 40%. Now your training was 90%, 95%. Your testing is 40%. Well, what happened? Well, you've overfitted your model, which means you've memorized the trends, and that's a problem, right? So it's like going to an exam, okay, and memorizing the exact types of questions, okay, and then as soon as the professor changes the question, then you're done. You can't really answer the question. So those models are really overfitted, and you don't want to build an overfit model. So that's why cross-validation becomes very important to make sure your data is split between training and testing to make sure your model performs right. And also, it is also recommended to also apply on a blind set, like another set of blind data that the model has never seen before. apply it one last time to make sure how your model performs on the blind data, and then to make sure your model still holds. So cross-validation prior to training your model becomes very, very important, okay? And then the steps 5 and 6, we already talked about those, which is, normalizing your testing set or your blind set or whatever you want to call it, and then testing the algorithm on various blind sets to make sure your model holds. And then the last step is, you can do a sensitivity analysis and to find pattern within the data, which we'll show you in this example. Or you can deploy the model real time, and that's the future in the oil and gas industry, to build, very powerful models to be able, in an attempt to be able to deploy those models real time, okay, real time. And I have the reference at the bottom in case you want to read up more on it. So now let's go and to just show you the equations for feature normalization and feature standardization. Feature normalization, as I said, is taking x minus the minimum of x divided by max minus minimum of x, which will transfer your data to have a scale between 0 and 1, okay? And then feature standardization is taking your x minus the mean minus the average of your data set divided by standard deviation of your data set. That's standardization. As I mentioned, some algorithms are recommended to use feature normalization, and some algorithms you recommended to use feature standardization, such as the distance-based algorithms. Now, as I said, the key to success, and I truly believe in that, and I think we have a lot of smart people, intelligent people out there. You guys are everybody that's listening today, you guys are very intelligent people. A lot of you guys are probably engineers. The key to success in machine learning, from my limited experience, okay, is combining domain expertise and the statisticians, okay? Do not hire, for example, somebody with a lot of domain, experience and no mathematical background, and also vice versa. Do not hire somebody with a lot of statistical background and no domain expertise. If you want to do that, it's completely fine. Just make sure you put them together. You get the domain experts in that field, and you combine them with with somebody with very strong statistical and mathematical background. And that's the key to really developing a successful machine learning model. So I can't really emphasize that enough. It's very, very important to truly combine these two people together to add value, okay? Now I'm going to talk about two algorithms, okay? First one is called k-means clustering, okay? K-means clustering, as I said, is one of the unsupervised machine learning algorithms, okay? And what we did here, we used k-means clustering to cluster the data into two statuses, okay? One, whether a gas well is loaded versus unloaded, okay? As I said, some of the other applications, of using clustering techniques in general, such as k-means, is type curve clustering, and frac screen-out clustering, and so on and so forth, okay? So let's go over what k-means means. So let's look at this picture here. Let's start from the left-hand side. What you see here is, let's just say you have, you want to, use two clusters. You want to use two clusters to cluster your data. And where did I get two clusters? With that two clusters, you can do different techniques to get how many clusters you need. Or you can simply say, based on my domain expertise, to solve this problem, I would need two clusters, okay? So let's just say you want to have two clusters. What you do is you initiate these centroids or clusters, okay, randomly. And you can, carefully pick, where you want these centroids to start initially, if you would like to, you can easily do it in Python. But let's just say I'm gonna start these two clusters, okay, randomly. Then what are you gonna do is you're gonna measure the distance. And when I say distance, I'm talking about the Euclidean distance. You can use Euclidean distance. You can use different types of distances out there, okay? But let's just say for simplicity, I'm gonna use a Euclidean distance. I'm gonna calculate, the Euclidean distance from each instance okay, to each cluster, okay, and see and basically assign the ones that are closest to this cluster to green, and assign the ones that are closest to, you know, this red cluster to red. You know, so you're going to measure the distance between each instance to each cluster, from here to here, and from this instance to this cluster right here. And based on its distance, you know, you can see that, for example, this one right here obviously is closer to this cluster. So I'm going to assign these, I'm going to assign this data point right here to that cluster. And you're going to repeat the same step until every single point is assigned to each cluster. That's step number one. Step number two is you measure the distance within these instances that you just clusters. So I'm going to measure the distances between these instances, okay, and measure the distances with, you know, between these instances right here, and move this cluster centroid to the average of those distances. I'm going to move this, for example, to the average of these instances, and move this cluster right here to the average of these instances right here. So that's what I did here. I measured the instances here, and then I moved this cluster centroid to the average. Did the same thing for this one. Now what you do is, again, you measure the distance between each instance to that cluster and to the other cluster, and reassign these instances, okay? Measure distance from each instance to each cluster, from here to here, and from here to here, and reassign all of the instances again. And then I'm gonna take the average of those instances again, and move that cluster centroid to the average again. And I'm going to repeat this process, keep repeating this process until the cluster centroids are essentially, they can't move anymore, right? So these are my final converged clusters. Then, you know, the output of this model would be every single row of data that you import, okay, would be assigned to a cluster, would be either cluster, you know, in this case would be either cluster 0 or cluster 1, okay? And that's pretty much it. That's what k-means is, okay? As I said, you can, if you have no idea how to, you know, how many clusters to choose, there are different techniques such as the elbow technique, which is beyond the scope of this webinar, that you can use to cluster your data. Now here's an example. What we did here was we wanted to detect liquid loading, okay? To detect liquid loading. And basically you can see here that the green lines are basically what are the unloaded points, and the red lines are basically the loaded points. And this was all done using k-means clustering. There's a good paper by Ansari al that you can look into it. It's a very good paper that I recommend you like to read. Also, we published some of that also in this book as well. But what I'm trying to say is you can cluster your data between loaded condition, which is green, and unloaded condition. And we wanted this to be independent of Turner and Coleman. Turner and Coleman rates have, you know, these were developed, you know, back in the 50s for, you know, conventional vertical wells, you know. So we wanted to develop an independent model for you know, horizontal multi-stage hydraulic frac wells. So we divided the data and basically applied k-means clustering using 2 clusters, and basically after we applied the k-means clustering, we essentially plotted this data, which is gas rate over, you know, date, and you can see it did a very good job detecting, you know, your unloaded condition, which are green, and loaded conditions, which are in red. Okay, and once you develop this k-means model, applying it real time is super simple, because it's just simply taking, as a new data point comes in, measuring the distance between that new row of data to the distances of each centroid cluster to see which one it is closest to. If it's closer to cluster 0, you assign it to cluster 0. And if it's closer to cluster 1, you assign it to cluster 1. Okay, so this is one example of using an unsupervised k-means clustering to cluster my data and basically use that as opposed to using Turner and Coleman rates, which were developed back in the day in the 50s for vertical wells, independent of Turner and Coleman, independent of those. Next, let's talk about feature ranking. So we have a bunch of completions and geologic features, and I want to know which features have the highest or the most important impact on my model. Like, I want to know which features have the most important impact on my model. And in this case, we used random forest. So random forest is essentially a powerful ensemble supervised machine learning algorithm. And you can use random forest for classification or regression problems. What random forest is basically an ensemble of decision trees. As opposed to using a single decision tree, you can have many decision trees. Like in this case, we use 1,000+ decision trees. And usually as you increase the number of trees in a random forest model, it really improves the accuracy of your model without overfitting your model, because it takes subsamples of your data. It's like a bootstrapping technique that takes subsamples of your data, okay? So the best way to think about random forest is to think about an ensemble of decision trees, many decision trees. And you take an average, at the end to come up with the final answer. And so the features that lie at the bottom, at the top of the tree, those features have the highest, the most important impact on your output of the model. In this case, the output of the model was cumulative production per foot. So you can see right away, you can tell which features have the most important impact on your model. For example, in this case, cluster spacing and gas in place and proppant per foot had the highest, or the most important impact on the model. And some of the features at the bottom right here, those ones had the lowest impact on the model. So what I always tell people is, well, so what? What do I do with this? Well, you can tell right away that which features you can really hone in on, you can focus on to optimize. You know that cluster spacing and proppant per foot, these have very high importance on the output of the model. And your output is your production performance, which is very important. So you want to hone in on those features and try to optimize those features, okay? I wouldn't worry too much, for example, about shot density. Would I care too much about shot density in this case? Well, based on all the historical data that I have, like for example, in this case, it tells me the shot density is not important. So why would I, focus my energy on optimizing something that has such a little impact? I'm not saying don't optimize. You can still optimize it, but just remember, the bang for your buck is not much. These lie at the very bottom of the tree. So you can still optimize them, but I would first try to optimize the most important features that have such an important impact on your model first. Okay, so that's using random forest for feature ranking. Now the next one is an artificial neural network. Okay, so an ANN. The idea of an ANN came from neurons of the brain. As you guys know, we have billions of neurons in our brain, and the idea behind an ANN is to basically, you have an input layer, you have a hidden layer, and you have an output layer. Let's just go to the next slide to kind of show you in picture. So you have this input layer, which are essentially your input features. In this case, I have sand per cluster, I have water per cluster, I have number of perfs, stage spacing, cluster spacing, landing zone, well spacing, and so on and so forth. I have these parameters that, based on my domain expertise, based on my analysis, I found to be the most impactful. So I'm going to include those as my input features into my model. Okay, and then there's a hidden layer in the middle, and in this hidden layer you have these hidden neurons. Each red circle represent a hidden neuron, okay? And these hidden neurons are basically used to process your input feature and connect that to your output feature. And in this case, my output feature, for example, is EUR per 1,000 feet, okay? So the idea behind an ANN is to minimize a cost function. And what is that cost function? A cost function is simply defined as the difference between actual values minus predicted values, okay? Which is right here. I have the equation right here, okay? So if I'm trying to minimize this, you know, let's just say I'm gonna pass in and predict my EUR, okay? And my EUR turned out to be, let's just say, 1.5 BCF per 1,000 feet, okay? 1.5 BCF per 1,000 feet. This is from prediction. But my actual EUR was, for example, 2 BCF per 1,000 feet. Now, what this ANN model does, it goes back to every single one of these neurons. Every single one of these neurons have something called weights or coefficients, okay? It's gonna change the weights and biases of these neurons, okay? And then it's going to spit it back again to essentially predict again what is my new EUR after changing these weights and biases, okay? And now let's just say my new EUR is 1.7. Now we're closer to 1.5, right? So it's gonna continuously repeat this. It's called a back propagation algorithm. It's gonna continuously change these weights and biases until this cost function, which is also called a loss function, is minimized. And that's what you see here in this picture. You have number of iterations and you have this loss function. And you can see, at least you would hope to see a decrease in cost function or loss function, you know, as you in each single iteration, you know, and that's what we did. Like in this case, we ran it 40 times. On the 40th iteration, your model was optimized enough and we're happy with it. Now, the next step after you train a model, you can still, there are a lot of fine-tuning parameters within the ANN model. You have, for example, how many neurons are you going to use? You know, what kind of algorithm, what kind of, you know, are you going to use a stochastic gradient descent? Are you going to use, you know, an LBFGS model? You know, what kind of, you know, model are you going to use? Are you going to use, for example, what kind of activation function are you going to use? Are you going to use a logistic activation function, a 10H activation function? So you can see there are a lot of fine-tuning parameters just within the ANN model. So the next step is to do a grid search. A grid search optimization essentially goes through different combination of different parameters. For example, it's going to run my model with, let's say, 20 neurons and this activation function and this solver and this regularization. And then it's going to, you know, change the 20 neurons to 25 neurons, for like for example, and continuously just try different combinations of different fine-tuning parameters within the ANN model in order to optimize my cost function and also provide the highest accuracy on the testing set or on the blind set. Okay. So grid search, I'm not covering grid search in detail in this case, but I just want you to know, once you, for example, train a model, the next step is to really put in the time to really try to optimize the fine-tuning parameters within each model to make sure your model has been optimized actually, okay? So now, just remember that, you know, this is, for example, we used Seaborn library in Python. It's an open source, free, you know, library in Python that you can use to use a pair plot in this case and a heat map. And on this hand side is just showing the relationship between the scatter plot between each input versus one another, you know. So you can find, for example, if you had anomalous points, you can clearly see the anomalous points and question those anomalous points or remove them prior to training a model. Then on this right-hand side, we're using a Pearson correlation coefficient. And what Pearson correlation coefficient is simply covariance of x comma y divided by standard deviation of x times standard deviation of y, okay? So the best way to think about Pearson correlation coefficient is to think about R. That's basically your R, okay? So you can see each input feature, for example, and the Pearson correlation coefficient is inside of each square, okay? So like in this case, you can see that, you know, there's a very strong correlation between, for example, Bach density, okay, Bach density, and gas in place. So it says which means the higher the gas in place, the lower your bulk density. So in this case, do I really need to, for example, include, bulk density in my model where I can get the same information from gas in place? The Pearson correlation coefficient is minus 0.97, so essentially giving me the same information. Why would you include two of the same parameters that provide you the same information into your model? Well, that's why you do a simple heat map, plot in your Pearson correlation coefficient to find the collinear parameters and remove those collinear parameters from your analysis. And that's a very important step, as we discussed in the workflow. Okay, so now you've trained a machine learning model. Okay, you're happy with it. Your testing accuracy is high. You've done all kinds of grid search optimization to make sure your fine-tuning parameters are optimized. You're happy with the model. You're smiling. Great job. Okay. The next step now is, well, now that you've trained a model, the beauty of this is that you can do a sensitivity analysis. Okay. A sensitivity analysis in terms of doing one variable at a time sensitivity. Okay. And when you train a machine, when you're done training a machine learning model, you can change one variable at a time to see the impact of that variable, okay, on your output feature, which in this case was cum per foot, or for example, EUR per 1,000 feet. Okay. And once you have, once you've done your sensitivity analysis, then you understand what is the impact of each feature on the output feature. For example, what is the impact of, sand per foot, or what is the impact of cluster spacing on the output feature? Okay, independently, one variable at a time. So here's what we did here. What we did was we trained a model, and then after training a model, we wanted to see what is the impact of increasing sand per foot from 1,100 pound per foot to 2,000 pound per foot on cum gas per foot. Okay, as you can see, it is increasing. So we can get we can understand qualitatively, and if the model has high accuracy, quantitatively, what is the impact of each variable on the target variable, which in this case was cum per foot or EUR per 1,000 feet. And on the right-hand side, same thing. What is the impact of cluster spacing? Okay, what happens as I increase my cluster spacing from, for example, 20 feet to 70 feet on the target variable, which is cum per foot. And you can see here clearly, as you increase your cluster spacing, your cum gas per foot is going down. So this is the beauty of once you train a model. Now that you understand what is the impact, going from this design to another design, okay, and you can change multiple variables at a time if you want to, once you train a model, if you're happy, if you're satisfied with the model. Now you can do your economic analysis to figure out what is my optimum completion design, okay, at different commodity pricing, because we know that commodity pricing has a huge impact on your design. The more expensive the gas or oil price is, the higher the gas or oil price is, it does justify pumping more expensive designs. Okay, the cheaper gas price and oil prices in these situations, it does not justify pumping expensive designs. So commodity pricing has a huge impact, and to do that kind of sensitivity analysis, you have to first build a model, train a model to your satisfaction, make sure it has high accuracy, make sure the model is a general model that does hold up very well when you apply it on testing and blind sets. And if you're happy, then you can do a sensitivity analysis to figure out what is the impact of each variable, or even changing multiple variables at a time on your your output feature, which you define based on what you're interested in. Okay. So with that being said, that's all I've prepared for today. I hope you enjoyed this talk, and I'd be happy to answer any questions that you may have. Actually, so I see some questions here. What is your suggestion, recommendation for a person that is going to learn a machine learning? Okay, so I would say the first thing is, to really read as much as you can first. Don't jump into just, going into, for example, Python and just trying to apply different algorithms blindly. I think that's a problem, right? If you just go in there and just learn how to program using Python and just apply different algorithms blindly without understanding them. First, understand and read as much of the literature as possible. That's what I did. The first thing that I did 5 years ago when I started was I went ahead and read a lot of different books and a lot of different papers and read different case studies. And I also tried to break down these algorithms into simple, in simple terms, and first solve these problems by hand. Literally on a piece of paper, I'm going to write down what does the ANN do, how I can change the weights and biases, and how I can really optimize a model by hand. To make sure I understand what Python, some of these Python libraries do. For example, the scikit-learn package in Python, which is a very powerful package, it has all of these libraries that you can apply different machine learning algorithms very quickly. Now, but first, before you apply those, you have to first understand, what's in these packages. What are the fine-tuning parameters? How do these fine-tuning parameters impact your model? So my recommendation is to read as much as you can first. Once you're, get a good knowledge, good understanding as far as how each algorithm work, then go in and, learn how to use Python or whatever, coding platform that you want to use. Okay. And then use those, use Python and try to practice with it. There are a lot of online courses you can take. There are a lot of different classes, different training courses that you can take. But I would first definitely start off by reading first. Question number 2. What are the current problems and challenges in the oil and gas, that machine learning or AI can solve? So some of the problems that I just said were, one was, the completion design optimization. Number 2, you can use clustering for different applications, liquid loading, type curve clustering. You can use it for screen out clustering. You can use machine learning for chemical optimization. You can use machine learning for plunger lift optimization, for intermittent wells optimization. You can use machine learning for time series forecasting. You can use machine learning for screen out prediction. You can use machine learning for km per foot forecasting. There are so many different applications. These are just some applications. A lot of applications in seismic interpretation. You can use machine learning for seismic interpretation with a lot of data sets. And a lot of good classification problems that you can use using machine learning. In this case, this whole problem that I've solved here, this was all regression problem, which means your output is a number. Okay, you can solve classification problems where your output is yes or no, true or false, good or bad, for example. Okay. So let's go to question number 3. For liquid loading k-means detection example, are we using just 2 variables, rate and time? It just comes across this way from the slide. No, we're not using just rate and time. And I'm sorry, what I was showing in that slide, I was showing just the result, just plotting, gas rate over time and showing the clusters. The variables that we used were gas rate, casing pressure, tubing pressure, line pressure, and water rate. We use these 5 variables as the input into the model, and we cluster the data. Now, before we cluster the data, you have to pre-process your data and apply some type of manipulation and massage your data to get it in a format that you'd like to. And then once you're done with that, then you can apply the k-means clustering to that. Okay, number 4. Appreciate the presentation. Okay, which package is easier to work with? Logging in real-time data, R or Python? Again, this is a preference question. That's a good question. I personally prefer Python myself, but it does not mean that you should also use Python. I strongly recommend to use whatever you're comfortable with. If you can learn both packages, more power to you. But I personally prefer Python myself, especially for some of the packages in Python, some of the libraries that I've used, the TensorFlow, scikit-learn packages, the visualization packages that I mentioned, Seaborn, Plotly, Matplotlib, Cufflinks, these are very powerful packages that you can use. Can AI finally provide an equation to be used for prediction? Yeah. So it's not going to be as easy as just providing like an equation. If it was a multilinear regression problem, sure, you can get your equation and apply that. But what a lot of companies do now, once you train a model, let's say within R or Python or whatever programming language that you use, you can apply that model on an edge device, okay, real time, and deploy that model on a real time basis, okay, and deploy that model on a real time basis. So it's not as simple. Now, some of the algorithms, like for example, if you use a neural network with one hidden layer and multiple neurons, sure, you can go through the process of extracting the weights and biases from your model and then just do the matrix multiplication and applying the activation function, and solving that problem by hand. But as if you train a model with 1,000 neurons, you really don't want to do that process by hand. So you want to deploy that model, that Python model, save that model and deploy it real time through an edge device. Okay. What else? Which package is easy? Okay, we talked about that. Based on your experience, do oil and gas companies prefer to outsource their data science related projects or use their own internal engineers? Okay, that's another good question. So when we first started, I mean, there are a lot of people that have been doing machine learning for many decades, and back then when Python libraries were not as powerful, and you had more luck outsourcing the projects, and really, because you didn't want to have a full staff for that. But nowadays, a lot of these major companies are having their own data science team on staff to tackle a lot of these problems. So I think as more companies realize the true potential of data analytics in general and just collecting that data, and going to apply those data to different problems, I think it becomes more and more relevant to have a full-time staff work within the company. So I think it really depends on the company, and the size of the company too has an impact on that. The bigger you are, the more likely it is then you have a full data science team as compared to smaller you are. So if you're, for example, thinking about doing projects, you probably you could have a lot of success with smaller companies that don't have a full data science team on staff. Okay, but I'm not discouraging you from tackling any other customer. I'm just saying that people don't have a full-time people on staff. You might have a much hard, easier time convincing them. What else? So what are some examples of classification, logistic regression in the oil and gas industry? Classification problem, you could solve some of the plunger, for example, plunger lift optimization. You could divide it into different classifiers. That's one example that you can use classification problems. You're going to have probably multiple if you're trying to understand the root cause of a problem. You can always do classification problems. Logistic regression, again, it's a pretty simple algorithm, but if it gives you a good answer, why not? What else? Is it possible to incorporate domain expertise or physics in machine learning, or is it a step Addressed in the machine learning design, feature ranking process, and post-training results, QC. So if I understand your question, is it possible to incorporate domain expertise or yes, absolutely. I mean, that's the whole point of having that domain expertise, to really, use that domain expertise to have an impact into your model. And the reason I say that is because, I think many years ago, somebody, they gave a very, simple problem to a statistician, with no domain expertise, and what he did was, after so many trial and error, he came out and said that API had the most important impact on the production performance. And then it turns out that the higher the API, the newer the well, is, right? So what they did was, so he said the higher the API, the better, the better the well. But in reality, API should not have been even included in the model. API is just a well number, well identifier, But the higher the API was, those wells were newer wells with, newer completion design, and as a result, those wells had better results. So, but that's what happens when you do not incorporate domain expertise into your analysis. So let's see. And I think these are all the questions, if I may.
Okay. Once again, thank you, Mr. Belyadi, for a very interesting presentation, and all the participants for taking part in this event. Just for information, a recorded version of today's webinar will be available in the APPIH social networks by end of today. Thank you very much and have a great time.
Thank you very much, guys. Appreciate it.